Okay, so since we finished our two examples of electrophilic aromatic substitutions, we're going to look at a different type of substitution reaction, which we would say is aliphatic. So if something is an aromatic, if it's an alkane, it's aliphatic, meaning that it doesn't have the aromatic group. It's a lot of single bonded stuff. So, and this topic is one that I remember we spent a good month on in a full year organic course, talking about the different things that would give us SN2 reactions versus SN1 reactions, the solvent effects, the substrate effects, the leaving group effects, the nucleophile effects, and what made it even more complicated than that is, in addition to substitution reactions, a lot of times the same reagents can have a competing elimination reaction. So don't be too scared. We're going to keep this fairly simple and just talk about the most direct and most straightforward examples of SN2 versus SN1 reactions, so you have a little bit of a background in this, as you would expect from an introductory class, and we aren't going to go into excruciating detail. There are some pages to read here, and this is quite a bit of pages. They'll define new terms for you like leaving group and nucleophile, and talk about what SN2 means. And if you haven't had a lot of kinetics, the bimolecular versus unimolecular distinction is one that you should pay maybe a little attention to make sure you know what they're talking about. So you'll find this stuff in Chapter 9, some substitution reactions that are worth looking at. Good preparation if you're going to go on to a full year organic class. Now the SN2 reaction, the 2 here means it's bimolecular. That means there's going to be 2 reagents in the most important step. So 2 reactants in the most important step. The one that's going to cause the reaction is going to be the slow step that determines the rate and everything else. And the thing is with an SN2 reaction, it's a very direct thing. You have something that's a very good nucleophile. So the N here means nucleophilic. So when we were looking at electrophilic aromatic substitutions, we had electrophiles coming in and forcing some chemistry to happen. With SN2, it's a nucleophilic reaction, meaning we have a nucleophile coming in and getting involved with the reaction. And then the big S means substitution. So we're going to look at 2 molecules reacting directly to one of them being a nucleophile to create a substitution reaction, or to cause a substitution reaction. And one of the most important characteristics of SN2 reactions is, since you have 2 molecules coming together, it's going to be pretty crowded. So what we're going to need is a reactant that's very exposed. So the thing is, right here, we have a primary carbon. So this is a primary bromide. So the primary carbon or primary bromide, and it's weird because I'm using this arrow to say that's what it is. It's not an electron pushing arrow, but then I'm going to use an electron pushing arrow maybe on the same page, so you have to make sure you understand which arrow is doing what. So this is just saying this guy here is a primary carbon because he's only attached to one other carbon. The leaving group, the thing that's going to leave, is the bromine. So the leaving group is there. And what we would have to invoke a reaction is a nucleophile. And you should look in your book and see which things are good nucleophiles. But a classic would be something like sodium hydroxide. So sodium hydroxide, the anions are typically nucleophiles. So the anion OH minus is a nucleophile. So these are the things that are going to react. So if you have a primary carbon, it's nice and exposed. So there's plenty of room back here. Only hydrogens are in the way and they don't take up much space. If you have a good strong nucleophile, then this can essentially move in, hit this, and push off the bromide. So let's since I don't want this arrow to be confused with the mechanism arrow, let's go ahead and rewrite mechanism. Not an SN1 reaction. So go ahead and we had 1, 2, 3, 4, 5 carbons. 2, 3, 4, 5. 5 carbons with a bromine on it. So this is 1 bromopentane. And if we react this with sodium hydroxide, then what we have is in one step. So when you have SN2 reactions, often occur in one step, which makes this pretty much the easiest mechanism we're going to write. The hydroxide comes in, forms a bond to that primary carbon, and then in order to make room for that, the bromine gets pushed off. So in one nice, slick, easy step, you end up with an OH in the position where you used to have a bromine. So now the anion bromide gets kicked off. Notice how it took its electrons with it, became a bromide, and then so the sodium plus, which is our spectator, will just hang out with the bromide where it used to hang out with the hydroxide. So that's a nice prototypical SN2 reaction. It's one step. The one step involves 2 molecules, so that's why it's 2 is for bimolecular, or 2 molecules are involved in the important step, the only step in this case. So we did a nucleophilic substitution. I should write out that the nucleophile is the hydroxide. So the OH minus is going to move in and push off the bromide. The bromide is the leaving group, and I mentioned that before. And so if that's the nucleophile, it makes the alkyl bromide the electrophile. So there it is, SN2 reaction, nice one step. And what favors SN2 reactions? Primary carbons, because there's room, spacious, strong nucleophiles, because they literally have to push the leaving group off. So they're sort of like bullies. Alright, so that's a little overview in an introductory sense for SN2 reactions.